paw graph. Here we go. So, as I draw the paw graph, and I'll use green to number these vertices. And I don't know why I chose 0, 1, 2, 3, but okay. Somebody who spends too much time programming. And we'll do the distance matrix. Okay. And if we're really lucky, we can even get the distance on our first try. And it's not too bad. So there's our distance matrix. Okay. So does anybody have a nice labeling in mind for our paw graph? This one turns out not to be too bad. In fact, I claim you can do it with length 2.
0.
All right, so you said 0, 0, 0, 1. Maybe you can't do length 2, but you can do it in length 3 for sure.
1, 0. No, that's distance 1. Oh.
Well, you can make this one a 1, 1. I think maybe we need length 3.
Definitely can't do it too.
All right, apparently we definitely can't do it in 2, but that's all right. D, 0, 1. Okay, there we go. All right, good. 3 is good. 3 is better than 2. Now.
3 is better than 4.
We're doing an induction argument.
Okay.
Okay. Well, so here's the idea. I want to show how a labeling relates to the distance matrix. And the way we'll do it is we're just going to grab one entry at a time. So let's go to all the first entries. And we're going to make a little matrix that corresponds to our first entries. And just to help us, I'm going to use the actual labels. Put them on the side. 0, 0, 1, 1. 0, 0, 1, 1. Now, think about the labeling problem. When do we get a contribution to a distance between two labels?
There's no D.
Well, there has to be no D and they're different, right? So what you can do is you compare the label on the row to the label on the column. So if one of them is 0 and the other is 1, or vice versa, then in terms of the distance in the graph, that means you would increase that by 1. So what we'll do is we'll do that here. So we say, well, it's not going to be very exciting, but I can think about how the first index is affecting the distance between labels. All right, so that's what we have there. Now, what's the second thing we should look at? Well, yeah, the second coordinate. So we're going to now look at the second coordinate. So, here we go. Again, we'll label on the side, so we have 0, 1, 1, 1, and 0, 1, 1, 1. Okay, and every entry I'm going to put either a 0 or 1. 0 is, well, it's easy to say when we get a 1. 1 is when you have your row is 0 and column is 1 or vice versa. So it will look like 0, 1, 1, 1, and then 1, 0, 0, 0, 0, 0, 0. Okay, so there's our second matrix. That corresponds to our second entry. Now, one more matrix. And well, maybe I have a highlighter that's different enough. Yeah. Here we go. Oh, yeah, even better. Bleh. Okay, our third entry. Now we're going to make our third matrix. And our coordinates are D, D, 0, 1. D, D, 0, 1. All right, so this is the first time we actually have some D's involved. So what's the first row? Starts 0, and then 0.
It's all 0.
Yeah, it's all 0, because it has a D. What about the second row? All zeros again. How about the third row?
0, 0.
0, 0, 1. The last row?
1.
Yep, 0, 0, 1, 0. All right, now, our great, we look at this and we say, what would happen if you added these three matrices together? And why would that happen? Right.
It's only counting the number of 0, 1, and 2s of each.
Right. So what you do is when you add these up, you're saying, okay, that between the pairs of labels, how many times do they have a 0, 1 difference? And so we said, oh, so a labeling is really breaking down our distance matrix into a collection of 0, 1 matrices. But not just any 0, 1 matrices. These are 0, 1 matrices that we might recognize. Have we seen these types of 0, 1 matrices before?
They're bipartite.
They are bipartite. And in fact, you can go one slightly smaller step further. Not only are they bipartite, but they're a very special, nice type of bipartite. I'll cover that one up just to sort of like not have you. They're complete bipartite. Now this one you might say, whoa, Steve, it's not complete bipartite. But it's almost complete bipartite. It's complete bipartite and isolated vertices. So if there's these, you get isolated vertices. So these form complete bipartite graphs with isolated vertices. And that's if you think about these as the adjacency matrices. Now, again, let's stretch our minds back ever so slightly. What are the eigenvalues like for complete bipartite graphs? Now, isolated vertices, you get 0. Okay, so get a bunch of eigenvalues of 0. But if I have a complete bipartite graph, what can we say about the eigenvalues of a complete bipartite graph?
You get a lot of zeros.
Lots of zeros.
And then square root of, plus or minus square root of n plus n.
Right, the square root of the product of the two sizes. Yes. And good. And there's one more eigenvalue.
I said plus or minus.
Oh, yeah. Okay, you said plus or minus. Good. Well, I didn't. So good. You were ahead of me. Excellent. Excellent. All right. So it turns out that these matrices are very simple. So each matrix has, if I can spell matrix, has one positive and one negative eigenvalue. And so a labeling is now a decomposition of our graph into these nice pieces. But moreover, it's a decomposition where each one of them has only one positive eigenvalue and only one negative eigenvalue. And now if you do a little bit of linear algebra work, and I'm going to skip the steps because I've embarrassed myself if I try to do it live in front of a studio audience. But essentially the punchline is, how many positive eigenvalues could I have if I added a bunch of matrices, each one having only one positive eigenvalue?
Yeah.
Well, I was hoping it was vague enough that it would be like, So because we know each one of these has a single positive eigenvalue, it says something about what the sum of them can have.
What's the relationship between, like, isn't there essentially no relationship between eigenvalues and sums of arbitrary matrices?
Well, the eigenvalues, yes, but we're talking about the signs of eigenvalues. So there's something called inertia. And that you can say a little bit about the inertia of a matrix. So inertia says number of positive eigenvalues, number of negative eigenvalues, and then everything else, also known as zero, is the everything else. And so it turns out, okay, I'll just get to the punchline. If I'm adding a bunch of these up, then the sum of these, say if I have 3 of them, hypothetically, well, that says that the sum of these can have at most 3 positive eigenvalues. And then the sum of these can have at most 3 negative eigenvalues. And so, if you look up our Graham-Pollock theorem, then, and I hope I spelled Pollock correctly. Let's see, how did I spell it last time?
That's how you spelled it last time.
Oh, good. Well, at least I'm consistent. I don't know if I'm consistently right or consistently wrong, but I am consistent, and that counts for something. So the Graham-Pollock theorem builds off of this idea of this decomposition, and it says, okay, so the minimum size of a labeling is greater than or equal to the min of the number of positive eigenvalues of D and the number of negative eigenvalues of D. And what's happening is the size of the labeling, if you want the minimal labeling, it's the minimal way you can rewrite your distance matrix as a sum of these 0, 1 matrices, each one being the adjacency matrix of a complete bipartite graph, possibly with isolated vertices. And you say, okay, so now it's just a matter of saying, well, what can you say about the eigenvalue structure here? And the answer is, the eigenvalues themselves, you can't say a lot. But in terms of the number positive and number negative, you get bounds. And so that says, I could have at most 3 positive eigenvalues if I'm adding 3 of these together. I could have at most 3 negative eigenvalues if I'm adding 3 of them together. And so that says, okay, so you get a bound in your labeling size using information about your matrix. This is not the way that people know the Graham-Pollock theorem. Almost nobody, if you say Graham-Pollock, will say, oh yeah, distance matrix. So let's talk about what the real Graham-Pollock says. This is actually the real Graham-Pollock. So let's talk about the Graham-Pollock that, if you are hanging out at a cocktail party and it just like casually people struck up conversation, said, how do you feel about the Graham-Pollock theorem? And you start saying, yeah, distance matrices are cool. And they're like, distance matrices? What are you talking about? That's not Graham-Pollock. Okay, so here's the usual statement. And we'll show how it's a special case. So the number, if Kn is edge decomposed into complete bipartite graphs. Okay, so I want to pause here and just talk about what's going on here. So edge, we're taking the edges of the complete graph and we're splitting them up into smaller chunks. Each chunk is itself a complete bipartite graph, possibly with isolated vertices. We're okay with isolated vertices. But other than that, everything looks like a complete bipartite graph. So that's what we mean by edge decomposition. So we're taking our complete graph, splitting it up into complete bipartite graphs. That's our assumption. The conclusion is that the number of bipartite graphs that we need is at least n minus 1. Okay, that's the conclusion. So it says that you can't be too small. Now, you can, of course, be very inefficient. Let's try an example with K5. So I'll draw K5 here. So what can we do? Well, one thing we can do is we can say, if we were trying to do this super inefficiently, what's the worst case scenario? How many bipartite graphs would we need? Be as inefficient as you can possibly imagine yourself being. Yes, number of edges, 10. Exactly, because each edge is a bipartite graph. It's K11. So we could be as bad as 10. Okay, could we do better? Yes. The claim is we can get down to 4. We can't get down to 3, because it turns out 5 minus 1 is 4. All right.
Does it claim that you can actually do it in n minus 1?
Well,
Or just that always at least n minus 1?
it's always at least n minus 1. You can do it in n minus 1. I'll show you one strategy. The strategy is called pick a vertex. All right, so we'll pick a vertex. Hey, I found one. And now, make it a star. And what do you see? Well, you've covered everything with that vertex, and what's uncovered is a k n minus 1. And so what do you do on that one? You pick another vertex. Doesn't matter which one. And you make a star. And you just repeat. And so you can, doing that, very quickly run out of things, but that's okay. The good news is we won't run out of choices before we run out of colors. And so you can always do it in n minus 1. Now the thing is, you don't have to do stars. You can do this in other ways. And so that's one of the things that's very surprising is you're like, well, maybe it's because you're stars. No. You don't have to just be stars and still get away. So for instance, you could try something along the lines of the following. And let's draw K5 again. And now what we can do is we can come down here and we can make ourselves a K22. Okay, so that used up 4 edges. Great. And that's pretty good. Then I can come to the top vertex, that hasn't been touched, and use all those edges there. There's another 4 edges. So now with just two complete bipartite graphs, I have 8 out of 10 edges. The thing is, the last 2 edges are apart from each other, and so I still need 2 more. Now you might say, well, okay, it's K5. Maybe if you get up to K9 or something, maybe then you can be more creative. And Graham Pollock says, no, it's not happening. Okay, so how can we prove this version of Graham Pollock, the one that people will like, or people will know? So, give you a hint. What's the distance matrix for K5? Lots of ones. Is it all ones?
J minus I.
J minus I.
Yeah, it's J minus I. This looks familiar. Have we seen this before? It's the adjacency matrix, yes. Do we know the eigenvalues? What are they? Yeah, so the eigenvalues of Kn are n minus 1, and there's just one of them, and there's negative 1 to the n minus 1. So now, what's happening here? Well, here's the thing, is I talked about how when you split your distance matrix up into a collection of disjoint, well, I shouldn't say disjoint, into a collection of complete bipartite graphs, but the opposite's also true. If I have a collection of disjoint bipartite graphs, which is what we're trying to do here, and put them together, it's the same process. And we say, okay, well, look at how many positive eigenvalues there are. Well, 1. How many negative eigenvalues? N minus 1. And so there's a min labeling here, and it says we need n minus 1. And what I should have said, I didn't say it very elegantly, is when we're thinking about decomposing the complete graph into complete bipartite graphs, we're really making labelings. And so, for instance, this K22, you'd have a 0, 0, 1, 1, D. And so the way you put a labeling is, if you have a complete bipartite graph, one side is 0, the other side is 1, anything unused is D. And so that's the Graham-Pollock that everybody knows. Now, why do they talk about this? Well, for one thing, it's kind of a really cool statement. And another thing is, it seems this is very combinatorial. And combinatorial things should have combinatorial proofs. Except they struggled. It took them decades before they came up with a proof for Graham-Pollock that did not use linear algebra. So all the nice proofs, all the proofs that you'd like to take home to meet your family, they're all linear algebra proofs. And so in the last 10 years, they finally came up with some counting proofs. And sometimes the counting proofs are questionable about whether or not they're really just linear algebra proofs in disguise, but the point is, linear algebra is good. It's a good thing.